we are going to use two of the big ideas that we looked at in our last video. The inverse trig antiderivatives and also the completing the square. Alright, so remember that integrals help us find the area of different regions. Alright, but area is always positive. So if anything's below the x-axis, we need to make sure it's taken care of with a negative when we're finding area. So find the area of the region bounded by the graph of this. Alright, now let's think about this function. Will this function always be positive? So it will always be positive because this is positive, so is this, but only in its domain. So let's see, what is the domain of this? Remember, that has to be greater than 0. 3, whoops. So if we take out an x, we get x minus 3 minus x. There we go. So remember, this is a parabola facing down. It would be crossing through 0 and also 3. So the domain is between 0 and 3, not including them. Alright, so anywhere in that domain, this function is going to be positive, which will be helpful because now we don't have to worry about it making it negative. Alright, so let's see, 1, 2, 3. Our function is only in between 0 and 3 because it's only positive. Alright. X equals, so our function, I have no idea what that looks like. I just know it's positive. Alright, yep, sure, I'm sure it's something like that. Not important, because I know it's positive, and I'm not going to do this geometrically. Alright, 3/2. That'd be right about here. That's 1.5. So here's this line, x equals 3/2. X equals 9/2, or 9/4 would be a little bit further. So I'm looking for the area of the region bounded by the graph of this, the x-axis, and these lines. So now I can just do this. Area equals the integral from 3/2 to 9/4 of this function, 1 over square root of 3x minus x squared dx. This doesn't look like something that I can do right now. Alright, so this is where what I said earlier, completing the square part comes in. Alright, so I'm going to rewrite this as this. Okay, I'm leaving space because I know I'm going to have to do something to it. So half of 3 is negative 3/2 squared would be positive 9/4. Now I can't just change the equation, right? But that negative's in the front. So really I just minus 3/4. So to counter that, I have to add 9/4. And I'm going to just write it like this, 9/4 minus, and the reason why I did that is because this part can now be factored into x minus 3/2 quantity squared. So back to our problem, I can rewrite this. 3/2, 9/4, 1 over square root of 9/4 minus x minus 3/2 squared. Alright, and I'll just put my dx on the top, save a little bit of space. Alright, if this was the case, a would equal 3/2, u would equal x minus 3/2. Alright, du would be just dx, so we're good there. So now I just use my formula, okay? Inverse sine of u over a, so x minus 3/2 over 3/2. And I'm going to evaluate this from 3/2 to 9/4. Alright, so the 9/4 part wouldn't be too bad. So 9/4 minus 3/2. That would just be 3/4. And then instead of putting divided by 3/2, I'm going to put times 2/3. Alright, minus arc sine or inverse sine of 3/2 minus 3/2, which is just 0. So now, let's see, simplifying this, I get inverse sine of 1/2 minus inverse sine of 0. So where is sine equal to 1/2? That would be pi over 6. And where is sine equal to 0? That's at 0. So the area of the region is this. And you can check that by using your calculator. Alright, yet another strategy. Yippee! Alright, when when you see that the degree of your numerator is greater than or equal to the degree of your denominator, you're going to be able to use long division to simplify the problem, make it more usable. All right. So over here, I'm going to use long division. X squared plus x plus 1 divided by x squared plus 1. All right. X squared times 1 gives us x squared. 1, change your sign, so we get x. So now x squared can't go into x, so I just write it like this. Okay, the reason why I'd want to do that, because now I can rewrite this integral as this, and I can do each part, alright? So the antiderivative of 1 is just x. This one, I notice that as, like, x is the derivative of x squared plus 1, off by a factor of 2. So I can correct that by doing 1/2. Okay, and then it's just ln of x squared plus 1. Even though I don't need absolute value because that's always positive, there you go. Alright, second one, we could do the same thing. X cubed minus 3x squared plus 4x minus 9. We have x squared plus 3. So that would be x. We'd get x cubed, and we'd get 3x, change the sign. Negative 3x squared minus 3x minus 9. Minus 3, so then I'd get minus 3x squared minus 9. Change our signs, and I get negative 3. Oh, I can't add. 4 minus 3, that's just 3, isn't it? Plus x plus x. Glad I caught that. So then we get plus x over x squared plus 3. Alright, I can rewrite that integral now as x minus 3 plus x over x squared plus 3 dx. Integral of x is 1/2 x squared. Integral of 3 minus 3x. This one, again, I recognize the x squared plus 3 in the denominator. The numerator is off by a factor of 2. So I'll correct it by putting the 1/2 ln absolute value x squared plus 3 plus c. And that's our answer for that. So kind of neat. We have a couple different strategies. We'll try a couple more. Ooh, trig. So you can use U-Substitution or pattern recognition. Now I recognize that cosine is the derivative of sine. So this is going to simply be a power rule thing. Okay, add 1 to the power. So we have sine of x. Add 1 to the power, divide by the new power. Don't forget your plus c. That was pretty good. Alright, this time it's almost the same. We have the derivative of the inside function, and we have sine of x squared. So we're going to apply the power rule again. Alright, it's going to be sine of x, add 1 to the power, divide by the new power, plus c. Not bad. This one is going to require some memorization. Okay, there is a power reducing or half angle identity. So if you have, not half angle, sorry, power reducing, you can replace sine squared of x with 1/2 1 minus cosine of 2x. Alright, and the other one, if you want it, cosine squared x, you can replace that with 1/2 1 plus cosine of 2x. So those are two different identities. They're the power reducing identities, and that's something that we're going to have to use, because you could change sine to 1 over cosecant squared of x. That's not going to help us at all, so we don't have the derivative of cosecant. You could also think about changing sine to 1 minus cosine squared x, but that doesn't give us anything because then we still don't have the sine. So neither of these are helpful for this problem. Alright, but this power reducing one will be nice because we have 1/2 times 1 minus cosine of 2x dx. Pull that 1/2 out to the front. The integral of 1 is just x. The integral of negative cosine of 2x, we have to correct for that. It should be, what I'm trying to say is I need to put a correction of 1/2 here. Antiderivative of negative cosine, is negative sign, okay, of 2x, and I put that 1/2 there to correct for that 2 if you take the derivative. And don't forget your plus c. All right, this last one I'm going to change color a little bit. So if you have an odd trig power, you can kind of think that as like an odd man out rule. Okay. What you're always going to have to do with these is leave one of the trig functions alone. Okay. Then you're going to have to make some kind of change, probably using a Pythagorean identity. And I know you wouldn't come up with this yourself, and if you do, that's great. But that's okay. I'm showing you, I'm exposing you to these different methods so that maybe you can use them in the future. All right, now if I multiply this out, I get sine of x minus cosine squared x times sine of x. And now I can just integrate. Antiderivative of sine is negative cosine of x. All right, look at this. I have the derivative of cosine is negative sine, right? And so I can just use the power rule here. So I'm going to put minus. I'm going to put that negative 1 as my correction. So add 1 to the power. Let me write my cosine function. 3 divided by the new power. Don't forget my plus c. So if you want to rewrite it, negative cosine x plus 1/3 cosine cubed x plus c. And you're done. All right, and so here is a nice simple one. This is one I'd like you to do for your WISP. All right, so it's not too bad. Go for it. You can do it. Okay. Now I'm going to probably finish up with these, and we can finish the rest of the notes another in class, or maybe in one more video. I don't know if I want to make another video. We'll see. Sometimes you have to use U-Substitution. Okay, so you want to be aware on high alert if you are off by more than a constant. Okay, if you're off by an x or a 2x or a 3 or an x squared, that's a case when you're going to have to use U-Substitution. Alright, so when you're off by more than a constant and when the inside function is linear or smaller. Okay, smaller is always helpful, but linear is even a higher clue that you have to use U-Substitution. Alright, so we're going to let u equal 2x minus 1. That means that du would equal to dx, or 1/2 du would equal dx. Now here we still have that darn x there, so we have to change something. All right, I want to solve this for x now. All right, so u plus 1 equals 2x, or 1/2 u plus 1 equals x. Now I have all of these pieces. All right, so that 1/2 from the du, I'm going to pull that out front. 1/2 integral. So I have, instead of writing x, I'm going to write 1/2 times u plus 1. Okay. Instead of writing square root of that, I'm going to write u to the 1/2 du. So I'm going to pull that 1/4 to the front. Oh, I can combine these now using the distributive property. That's just u to the 1. So that's u to the 3/2 plus u to the 1/2. And now I just use the power rule. So 1/4 times, and I'm going to leave this open for a second. I'll tell you why. Add 1 to the power, 5/2, sorry. Divide by the new power, 2/5. Instead of writing u and wasting time writing it again, I'm going to replace it now with my function. Okay, plus power rule again, add 1 to the power, divide by the new power. Instead of writing u, I'm going to write my 2x plus 1. And don't forget your plus c. So there you go. You can rewrite this in multiple ways. You can simplify it. You can factor out least powers. But I'm not going to take the time to do that right now. All right, let's try this next one. We're going to let u equal 2x minus 1 again. So du equals 2 dx, or 1/2 du. equals dx. 2x equals u plus 1. X equals 1/2 u plus 1. So it's not too bad. We're going to set it up similarly, okay? Instead of writing, this time, instead of writing this, I'm going to write, see that 2x minus 1, okay? I'm going to write that as u to the negative 1/2. And now look at this, I don't have x squared, right? But I do have x, so I can write that as 1/2 times u plus 1 quantity squared du. Alright, so I'll square that 1/2 and pull it out to the front. Then I can distribute, okay? But not until I multiply this out. So I'll get u squared plus 2u plus 1 du. Now I can distribute. So u to the, think about it as 4/2 minus 1/2, so that would be u to the 3/2 plus 1 minus 1/2 will be u to the 1/2 plus u to the negative 1/2 du. Okay, power rule. Add 1 to the power, 5/2. Divide by the new power, 2/5. Okay, plus add 1 to the power, 3/2. Divide by the new power, 2/3. Oh, I forgot my 2 there. Ooh, didn't want to lose that. So still have that 2 there. Okay, plus add 1 to the power would be 1/2. Divide by that new power gives us 2. Instead of writing u, I'm going to fill it in with 2x minus 1. Okay, so this is probably a pretty good place to stop. I do want to go over C, D, and E, these ones, in class. All right, and we'll probably talk about this area in class as well. These are good problems, so I'd like to practice it. All right.